Hello, hello, hello. Welcome back to Science While Gaming with me, Mr. S. Continuing our series on chemical reactions and equations, we are talking about net ionic and complete ionic equations. I am predicting this video to be pretty short because net ionic and complete ionic equations are very straightforward, especially if you've been paying attention to the rest of your lessons that your teachers have been giving you, which we all know you definitely totally have been and absolutely have not been goofing off at any point in the lesson. So just quick reminders on some things when it comes to chemical reactions and their equations and identifying which types. There are 5 types of chemical reactions: synthesis, decomposition, single replacement, double replacement, and combustion reactions. Between my other videos, your lessons in school, other videos that exist on YouTube and the internet as a whole, really you should definitely be able to identify all of these things at this point in your careers. So if you can, you're really going to want to get on that, because that ability is super important for basically like the rest of chemistry. Now, what I started talking about with complete ionic and net ionic equations, they're focused basically on 2 of the types of reactions. You're focused on single replacement and double replacement reactions, and hopefully you remember that those 2 types of reactions are basically like if you have a dance partner, you and your dance partner at the dance, and a person comes in and takes your place and replaces you with your dance partner. Now you are alone and they are part of a new dance couple. That would be a single replacement reaction. One thing got replaced in the reaction. Double replacement, it's you and another couple switch dance partners, so now 2 new dance couples are there. I know for some reason square dancing is big in schools, so it's like, I think when you promenade, that's when you switch partners. Whatever the call is for switching partners, it's like that. You're switching dance partners. That's the whole deal. It's not super exciting, but that's what it is. So with those 2 types, there's an additional thing that can and does need to be done sometimes. That is writing the complete ionic and then the net ionic equation after you've written the complete ionic equation. And what that basically means is you're going to take those 2 types of reactions, the single replacement and double replacement, and break it down into the actual individual ions that do any of the work. It's not to say that any of the ions in a single replacement or double replacement reaction are not important, because they really super are. They're like super important. But they don't participate in the actual chemical reaction itself. They're kind of like watchers. They're spectators, and they are in fact actually called spectator ions. I was just trying to think of a better way to describe them. The way that I've described them in the past is, if a chemical reaction is a football game or is a show, the spectator ions are important because they make it happen. If it's an away game, you need bus drivers to get the team to the game. Spectator ions are the bus drivers. They're very important. You can't do what you want to do without them, but they don't participate in the game themselves. So they're important to get you there, but they don't participate in the reaction. For a play, it's your stage crew. Stage crew is super important. Play can't go on without it. But sometimes when you build sets, you don't participate in the play itself. So you're not acting on the stage, and that's what we're talking about here. So if you're not actively participating in the reaction, then you are a spectator ion. So we need to be able to determine what's actually happening here and what's not. This is important to chemistry because we want to know what's the actual thing that's causing a reaction. What's really going on? Who's actually doing any of the work? If we want to recreate this reaction in the lab, what kind of chemicals can we mix together to make it happen? If we can identify which ions are actually participating, we can get those ions from multiple different sources. So if we start with one set of things mixing together, but we decide that we have a better way to get that ion, then you can have a better reaction. So knowing this is pretty important for that aspect. If you're going to a career in science, it's definitely going to be something you're gonna want to know. If you're not going into a career with science, it's still handy to understand thought processes and logic. So I suggest paying attention and doing your work anyway, but you do you. With these types of reactions that we're trying to focus on and learn and understand what they're doing, we need to be able to really explain what they are. And that might be the wrong set of terms to use here, because it's not so much explain what they are. What you want to do is identify them. In our writing of chemical reactions of any type, we've been adding, and I'm sure you've seen in your textbooks and worksheets that your teachers have given you, little symbols in the bottom right of the chemical formula that are inside of parentheses. It'll be S, L, G, or AQ. And those symbols stand for solid, liquid, gas, and aqueous. And it's the aqueous one that's super important to us for this whole complete ionic and net ionic equation process. Aqueous stands for dissolved in water. That's what it means. So when you have an AQ there, it means that you started out with a solid form of this substance and dissolved it in water. Surprise, surprise. So knowing what's going to dissolve in water is a different skill set. That skill set is known as being able to know and apply your solubility rules. And the solubility rules are a set of rules that tell you whether or not a thing is going to dissolve. That's what it boils down to. So if you know if something is going to dissolve or not, you can know if we mix it in a chemical reaction, is it going to be AQ or is it not? This is a thing that we are going to want to be able to do. If we can do that, we can figure out exactly what's going to go on in the reaction. We can break it down to find out what ions are involved. And this is a process that is specific to ionic compounds. So you are not dealing with covalent compounds that are made of only nonmetals. We're dealing with metal and nonmetal specifically. The solubility rules are expressed in a lot of different ways. There's really 5 basic rules, and I'm honestly not going to go through them because it's how your teacher wants to have you express them is often individual to that teacher. There are some things that are similar through all classes. Things like everything. If you have a compound made with something from column 1 on the periodic table, it's going to be soluble. And that's just a straight true statement. That is literally just how it is. If you have something with group 1 on the periodic table, then you have a soluble substance. Full stop, end of discussion. So those are the kind of rules that we're talking about. And so if you can know what those are and learn how to apply them, that's very important to this whole process. Most chemical equations, you're gonna actually just have them. We generally write chemical equations with the symbols indicating if they're solid, liquid, gas, or aqueous automatically. So a lot of the work that you're gonna get, you're gonna know that. The trouble will be when you have to predict the products in a reaction. You're given 2 solutions, mix them together, you produce new things, and then, okay, is this a chemical reaction? Did you make something, or is it just a nothing? The way to tell if it's a nothing would be to look for your different signs of a chemical reaction occurring, which we've talked about before, but just very quickly: production of heat or light, so energy discharge, it gets hot, it gets cold, so change in temperature, it produces a gas, you have a sudden appearance of a solid. Anything like that, that'll be an indicator a chemical reaction is occurring. If you have a chemical reaction occurring, you're probably going to be able to do a complete ionic or net ionic equation on it. So that's a long walk to get to the point of you need to know somewhere these 5 rules, because these 5 rules tell you if you can have it break apart. Anything that's written with an AQ in a chemical reaction is going to break apart, and it'll break apart into the ions that make it up. Best example that I have for you is when you take salt, like literally table salt, and you dissolve it in some water, it does not stay molecules of salt. It breaks apart. It separates into a molecule of the sodium ion and a molecule of the chlorine ion. So you will not have NaCl, but you will have Na plus with a charge of +1 and Cl with a charge of -1. We call those electrolytes, and I'm sure that's a term you've heard because we're in a world where commercials are all over the place and unavoidable, and Gatorade is a thing that exists, and they make a big deal about having electrolytes in it. And really all it means is that it's got ions. That's what it means. In this thing there are ions, which is great. Your body does need ions, but it's not like all of the time, and unless you are running around going crazy, you're not going to need to super replace them. If you just eat and drink normal, you'll be okay. But if you are running around crazy, by all means, have something that produces a little bit of electrolytes and get some in your body. It's not terrible. Regardless, these aqueous substances, things that dissolve, they're not actually in the full form. They do separate into the different ions that make them up, and that's the important thing to remember. You will have complete ionic equations that have them broken apart. That's the whole point of writing the complete ionic equation. You are showing the ions that can break apart as broken apart. So it's a very important thing to be able to know. If you can know your rules of solubility, you'll be able to identify what broke apart and what stayed together. And if you can do that, you will be able to write your complete ionic and net ionic equations. Pardon me. So the basic layout of these equations is when you have them mixed together and you have anything that's written as an AQ, then you split it into the things that make it up. And when you have something that's labeled not AQ, you leave it alone. And that's it. Just stop messing with it. Leave it alone. And just separate your ions, and that makes you a complete ionic equation. What I'm gonna do, because I feel like I'm failing just a little bit, is I'm gonna draw a little thing here. So that's zinc. We're gonna combine it with copper. I really should give myself an easier substance to do this with, but I'm already halfway there. So that's copper, sulfate, that's what I'm trying to do. So, when you combine zinc with copper sulfate, like this zinc, that's a solid. It'd have a little parentheses here with an S in the middle, and the copper sulfate, it'd have a little parentheses here with an AQ in it. What that means is that zinc is a metal by itself, and we don't do anything to it for our complete ionic equations or net ionic equations. But the copper, because it has that AQ, we are going to do something with it. We would actually separate it into the ions that make it up. So you would end up with Cu with a Alright, well that's supposed to be a 2, but I guess we'll just keep going then. Cu with a +2 charge, or 2+, doesn't matter where you put the plus, you just have to indicate it. Right, so this came out of here. Copper's got a +2 charge, and then you have your SO4. I guess I'm feeling real brave in trying to do this, so if you don't like it, deal with it. S. O. And this SO4 would have a 2 minus charge because it's -2, right? So when we want to write our complete ionic equation, you have Zn plus CuSO4, and it becomes Cu plus 2 and SO4 minus 2. So these two things have separated. It still came from the same substance. It is still the same thing, but it had to come from somewhere. That's where they come from. So anytime you have an AQ, you really do want to split it apart just like you see here. Now, what this doesn't explain is our net ionic equations. In our net ionic equations, you have, as I said before, spectator ions. These spectator ions are ions that are important to the reaction, because without them you can't actually have it, but they don't participate in the reaction themselves. So they're important in making the reaction occur, but they are not important in the reaction. And it's a small but important distinction to pay attention to. So when you write your complete ionic equations, you show your spectator ions. I can tell you right now, in the whole reaction of this zinc replaces the copper. Then you have solid copper and then zinc sulfate. Your sulfate, your SO4, that's a spectator ion. So when you write your net ionic equation, you want to write it without that sulfate. So you want to get rid of your spectator ions. The purpose of getting rid of them is so that way you can focus on the ions that actually cause the reaction to occur. In science, especially medicine, we want to know what ions are causing a thing to happen, because you can have so many different types of chemical reactions. If you can get an ion that is important to the reaction through a different substance, then it's going to help you in the long run, because you can have it in multiple different sources. And some sources of a particular substance, either a compound or an element by itself, can be dangerous to humans, and some are not dangerous to humans. And if you can get the same elements from sources that are not dangerous, that is very handy when it comes to making medicines. So when you write your net ionic equation, you still write, split up your AQs, get rid of your spectators, literally cross them off, and then rewrite what's left, anything you didn't cross off, and that's your net ionic equation. It's like the difference between your gross pay in your paycheck, so that's your paycheck before they take out the taxes, and your net pay, which is your paycheck after they take out the taxes. If you work a job and you've seen your paycheck in these two states, there is a drastic difference between them. And that's the deal with net ionic equations. The main difference between complete and a net is that the net misses that spectator ion. So if you can miss that spectator ion, you have a net ionic equation, and that just makes your life easier because you can focus on what's actually occurring in that chemical reaction. And that's basically it. The process is not hard. The list of solubility rules exists all over the place, so you can Google it, look it up. I'm sure you have it written down in your notes somewhere if you've been paying attention in your lessons in the classroom, because there's no teacher who doesn't cover this stuff that doesn't talk about complete and net ionic equations, because they are so very much required to do this. And that'll help you predict your products, if something's going to break apart or not, or if it should or if it shouldn't. And then write your complete net. Break everything apart that's AQ, cross off the things that are exactly the same on both sides of the arrow, rewrite whatever you didn't cross off, and you have your complete end-net ionic equations. As always, if you have any questions, leave a comment. You guys know the drill. There's not a lot left to cover here at this point. We'll be moving on to some other discussion, and who knows what it is next. Any questions, any clarification you might need, feel free to leave a comment. And that's all for now. I will see you later. Enjoy the rest of your day. Thanks for visiting. Bye-bye.